Dear students, welcome to my channel. Main topic of this video is indexing and scoring in information system and subtopic is sequential search. In this video, brute force algorithm, Knuth-Morris-Pratt algorithm and Aho-Corasick algorithms are covered under sequential search. Now let us start. Sequential searching is preferred when text is small, very volatile, that is continuously changing, not processed, and the main important point is index space overhead is not afforded. It is used for text searching when no data structure has been built on the text. The problem of exact string matching is given a short pattern P of length M and long T of length N, T is nothing but text or the string, and find all the text position where the pattern occurs. In this video, three algorithms are covered, that is brute force, Knuth-Morris-Pratt and Aho-Corasick. Now start with the brute force algorithm. It is the simplest and easy algorithm. It consists of merely trying all possible patterns position in the text. For each such position, it verifies whether the pattern matches at that position or not. Does not need any pattern pre-processing, and many algorithms use modification of this scheme, and it is going from left to right in a search. Now the given text is there. For simplicity, index start with the 1. So text is nobody noted notes and we require to find out the pattern not. Now initially I is 1 and whenever we start at a new location j becomes 1. Now n matches both increments, o matches both increments, but here mismatch happens. So when mismatch happens, at that time we require to make initialize j equal to 1 again and we require to shift I to a suitable location. Now here as first character is not matched, so we are, as this pattern is not matched and this pattern is started with the first character, so we are changing I to the 2. Then I is 2 and j becomes 1. Pattern does not match, character does not match, shift I, character does not match, shift I. So in this way we are shifting I continuously as first character of the pattern and the text doesn't match. Now at 8 location match happens. So first pattern found at when I is equal to 8. Now next time it may happen that the pattern may match from the next character, therefore we are incrementing I from 8 to 9. Now n and o not match, so in this way it will continue. At when I is equal to 14, 15, 16 pattern match, and after that we are again increment I to the 15 location, so that it may happen that the next pattern may present at this location. So in this way we are proceeding for the algorithm. So in this way three pattern are searched, but here unnecessary, that is there is no smart movement, that is I is continuously checking, and after that if not match then it will reverse back to that next location. There are O of n text position and each one is examined at O of m cost. The worst case of brute force algorithm is O of m into n. Now see the next example. Here the text is 6 times b and pattern is 3 times b. So pattern will be matched for 4 times. This is first, second, third, fourth and fourth. So here first I is 1, j is 1, b matches, bb matches, pattern got match. Now it will increments I from 2, then 2, 3, 4 matches, pattern got match, I becomes 3, 3, 4, 5 matches, then I becomes 4 and 4, 5, 6 matches. So in this way brute force algorithm work. Next algorithm is KNP, that is Knuth-Morris-Pratt algorithm. It doesn't provide a significant average speed up compared to the brute force algorithm, but like BF it uses a window that slides over the next but employs a more efficient strategy. After checking the window whether it matches the pattern or not, the algorithm identifies a prefix of the pattern that has already matched with the text. So that's why compared to BF algorithm, this algorithm is smart because it is using the prefix of the pattern that has already matched, so that very efficiently the I pointer increases when the pattern does not match or previous. Whenever the next I increment is there, then it makes a smart move. This information is then utilized to skip unnecessary window position during the shift, that is avoiding the redundant checks. KMP smartly reuses information from prior comparison, leading to a more optimized search process. Now here we are performing the pre-processing on a given pattern. So that is called longest proper prefix table. So this is the important step of KNP algorithm. So KNP algorithms works by pre-processing the pattern to create a table called longest proper prefix table, that is called LPP table. The LPP table stores the length of the longest proper prefix of each suffix of the pattern. This information is then used to avoid the re-examining the characters that have already been matched. Now we will see how that longest proper prefix table is created. Now pattern is XY and its longer proper prefix table, that is LPP table, is 00120. Now we require to start with the prefix and suffix pattern. Now we will start with the first two characters. Now the first two characters are XY. If we take the prefix of XY, then at that time we are getting when two characters are there, we are taking one less prefix and suffix. So when the character XY is there at that time, so when one character is there, by default the prefix is, this table value is 0. Now next we will take XY. So prefix is 1, that is nothing but X, and suffix is from this side, that is nothing but Y. So when two characters are there, XY, prefix is X, suffix is Y, they didn't match, so that's why the value is 0. Next we will take XYX. So for XYX we require to take 1 and 2 combination. So from the prefix side we will get X, XY, and from the suffix side we will get X and YX. So from the prefix X, XY, and from the suffix side X and YX. Now there is a match with 1, so that's why the value 1 comes here. Now we will take XY, 4 characters are there. So prefix and suffix can be possible of 1, 2, 3 characters. So prefix is X, XY, XYX. Suffix is Y, XY, and YXY. Now we can see that 2 character matches, that is XY, XY. Therefore its value is 2. Next is XY, XYZ. Now the prefix can be possible X, XY, XYX, XY, XY. And suffix can be possible as Z, YZ, XYZ, YX, YZ. So here we can see that nothing gets matched. So therefore the value of Z location is 0. So initially we are taking, for the first character we are taking the value 0. For next two combination we are checking the 1 prefix and 1 suffix. For 3 we check 2 prefix and 2 suffix, and maximum match we are mentioning here. That is nothing but what? LPP table. Now see the pattern PPQP. Now for the first we keep 0. Next is PP. 1 prefix is possible, which is P, and suffix is possible P. 1 match, therefore it is 1. Next is PPQ. So 2 suffixes are possible. 1 is P and PP, and suffixes are Q and PQ. No match, so 0 is there. Next is PPQP, then P, PP, PPQ. Next suffix are P, QP and PQP. So no match, only single character match, so that's why the value is 1. So this pattern and this pattern didn't match, so we are getting the 1. So in this way we are creating the LPP table. Now we will see this on the fast track. AB, ACA, initially it is 0. For the next, prefix is A, suffix is B, no match. ABA, AAB, ABA, only 1 match, 1 is there. Next time ABAB, ABAB match, so we are getting 0. So in this way we are proceed, and we check whether when the prefix and suffix match with the maximum characters, we will keep that number here. That is nothing but the creation of the LPP table. Now we will see how this LPP table is used when we want to slide the window from left to right. So now here 2 pointers I and J are used. I is for text and J is for the pattern. When character at I and J location didn't match, mismatch position is J. Number of character match is J minus 1. If J equal to 1, means if mismatch occurs at the first character, then new window position is I plus 1. Else we require to take new window position is I plus J minus 1 minus longest prefix table J minus 1. That is, we require to take this J where mismatch occurs. We require to add this J minus 1 location, and we require to subtract the LPP of j minus 1. So this is the KNP algorithm. Now we will see with the example. Text, given text is there. For simplicity we are starting the index with 1 and pattern is PPQP. So first we require to make the LPP table. So for the LPP table is 0 1 0 1. Now our I is 1 and j is 1. Now the first character match both increment, match both increment, both increment. So here the match occurs. So this is the first match. Now here it may happen that our pattern may be start at the second character again. So we are making I is equal to 2. Now from here you just give the attention. So in I is equal to 2 and we again start with j equal to 1. First character matches, and for simplicity I am taking only the next four characters according to pattern window size. Now PQ, next character, fourth character are PQPP, PQPP. First character match, second character mismatch. So mismatch occurs when our j is equal to 2. So j equal to 2, we require to make j minus 1 equal to 1, and new window position is equal to I plus j minus 1 minus p of j minus 1. That is, this is nothing but the prefix table. So I is 2 plus j minus 1 is 1, and the j minus 1, that is j is 2 and j minus 1 is 1, and at one location the prefix value is 0. So 2 plus 1 minus 0 is equal to 3. Now we increment I is equal to 3. Now here from I equal to 3 we are getting Q P P R. Now Q P P R. Now here mismatch occurs at the first character. When mismatch occurs at the first character, we are simply incrementing the I. Now I is 4. So from the 4 P P R P, 2 times match, third time mismatch. So j equal to 3, j minus 1 is equal to 2. New window position is equal to I, which is nothing but 4 plus 2, and at 2 location the value of LPP is 1, so minus 1, which is getting 5. So I is equal to 5. At I5 location we are getting PRPP, PRPP, and j equal to 1. PP match, mismatch, we are following the same. So in this way we are going continuously. So algorithm is very easy to understand. So in this way J6, J7, sorry, I6, I7, I8, and now here we can find out that the every time it is not smart. Now it is almost execution like BF algorithm. So there is no substantial gain. But in the next example we can see that the prefix table sometimes may give the substantial gain when we are sliding to the next location. So I is 10 is PPQP, match happens. So when match happens we are incrementing I by 1. So in this way we are just checking the window. So it is very important to understand first to create the LPP table from the given pattern, and when the mismatch occurs at the first location we are incrementing simply I by 1, but and when pattern matches at that time also we are incrementing I by 1. But when mismatch occurs when at I is not equal to 1 or I is greater than or equal to 1, at that time we are using this formula, that is I plus j minus 1 minus p of j minus 1. Now see the next example. Pattern is YZ YZ PX. So by using the prefix table we are first creating this value, and here now the pattern is YZ YZ PX. Now we will keep on this. So first pattern is at first location mismatch occurs, so we are incrementing I by 2. Now I is equal to 2 and j again start at the 1, and we can see that first time, second time, third time, fourth time mismatch occurs at the fifth location, so we are incrementing j equal to 5, j minus 1 equal to 4. New window position is 2 plus 4 minus, at this location the prefix value is minus 2, so we are getting 4. Now our I is 4, and here again we are checking from the I equal to 4, that is YZ YZ YZ. Then here again mismatch occurs at the again fifth location, so we are getting 4 plus 4 minus 2, that is same previous values are there. So 4 plus 4 minus 2 equal to 6. Now we are moving 6, 1, 2, 3, 4, 5, 6, and we can see that the pattern gets matched. So in this way the KNP algorithm works. Now the third algorithm is Aho-Corasick algorithm for pattern searching. Aho-Corasick algorithm is an extension of KMP algorithm, and it is specially designed to efficiently search for a multiple pattern in a text. While KMP excels at finding all the occurrences of a single pattern, Aho-Corasick extends this capability to handle the set of patterns simultaneously. Means Aho-Corasick is not finding a single pattern at one time but multiple patterns simultaneously. The key difference between the KMP and Aho-Corasick lie in their data structure and failure transition. KMP utilizes pre-computed, that is LPP table, to guide its pattern matching process. In this Aho-Corasick algorithm, it uses a tree-like data structure to represent the set of patterns and employ a more general set of failure transition. So in this example, when I explain the example, that failure transaction will get cleared. Failure transitions. These failure transitions play a crucial role in Aho-Corasick efficiency. When mismatch occurs during the pattern matching process, instead of restarting from the beginning, this is very important, and this is nothing but the gain of Aho-Corasick algorithm. Aho-Corasick utilizes this failure transition to quickly jump to the longer proper suffix of the currently matched prefix. This significantly reduces the number of character comparison and improve the overall performance. Now see, now in this algorithm the text is given, and text is AHISHERS. Now we require to find out the pattern he, she, hers and his. Now first we will draw the try pattern, and it is already covered in suffix array, suffix tree and even inverted file, how to create a try data structure. It is a very simple one. Now this is a root node. From here we can start the branches, for example HIS. Now from the HE branch will start, and from that HE will continue with the HERS, and new branch, that is with she, will start from the root, that is SHE. So in this way we are drawing the try data structure to represent these four patterns, that is HIS, HERS, SHE, and the he will subsume in the HERS. Now after that we require to draw the failure transition. So here the all failure transitions are not shown for the simplicity, but in the next example I can show you that where the failure transitions are going. Now here we require to check the longest proper suffix of the currently matched prefix. So it is checking the longest proper suffix. Now see here, now after HIS, now HS ends. Now after S, what is the maximum suffix can be possible? We can observe that after S 2 characters are there, that is 2 suffix locations are there. So this transition, after that is failure transition of S, is transmitted to here, that is SHE. Even again same for this S, the failure transition of this S is mapped to here, that is SHE. Now failure transition of this E is mapped to this E, because after that suffix pattern is there, RS. Now the failure transition of H mapped to this, then after that I and S are there. So in this way the failure transition are mapped. Now it's the same diagram, but only the numbers are given to understand. Now for 1 the failure transition is at 0. So for simplicity it is not shown, otherwise the diagram becomes very complicated. So for 1 the transition, that is here the longest prefix cannot be possible, so it is going to the 0. For 2 it is going to the 0. For 3 it is going to the 0. Now for 4 is nothing but H. Now you can see that after H, that longest prefix possible is IS and ERS also. So from 4 the failure transition is going on 1. So this diagram and this diagram is same. Then for fifth is E. After that E, this can be possible, that is RS. So this 5th is going to the 2. Then next is 6th going to the 0. 7th is going to 3rd. Now 7th is S. Now after this S can be comes after this 7th S, it will come to the this HE, that is this S and this HE, that's why comes here, and after that this 9th, this S ends, it will come to here again at 3rd location. So the diagram is are same, only we require to make the connection. So this is the way. When output function, when 2 is there, we are getting the one pattern HE. When 5 is there, we are getting the pattern SHE, and he also. When 7 is there, we are getting the pattern HIS, and when 9 is there, we are getting the pattern HERS. Now our text is given AHIS HERS. Then we are Aho-Corasick algorithm finding the pattern simultaneously. Now for this try data structure and for this given text, it will give the output as HIS first. Now HIS, this HIS, because in the text also A didn't match, so it will move to the null state, or it is not actually moving, it is again going to the null state because A didn't match with any branch. Next is HIS, so HIS, so we match with the 3 location HIS. Now after this S, it will goes to here because this null failure transition is given. So after 7th, it is not going to the root node, but it is going this. After that, it will map she, that is SHE, and in the she, the he gets match. So E is there. After E, it is not going to the null transition, but after E, it is going to the Rs. So it will match the HERS. So at the same time, that is in a single pass, so we are finding the HIS, SHE, HE and HERS. So this is nothing but our Aho-Corasick algorithm. If our pattern is given like this USHER SHIS, so at that time first it will find out the she and he, then from here it will goes to the hers, and from this here it will goes to the his pattern. So in this way the Aho-Corasick algorithm finds the multiple pattern simultaneously. So these are the references for this video. Thank you.